All right, I would say probably the most important lesson in this unit is all of the gas laws. Now, these are general gas laws. They apply to really all gases, and these are things that you probably already know, but we're going to put names to them, and you will need to know the scientists that actually discovered or interpreted these gas laws. In this case, most of the time I don't have you memorize the scientists, but these guys are pretty important because the laws are named after them. So these laws govern how gases work. Okay, so we're starting with Boyle's law. This is the pressure and volume relationship. So there's only one gas law that you need to know that has an inverse relationship, meaning as one goes up, the other goes down, and that is Boyle's law. That means as the volume goes down, the pressure goes up, or vice versa. I want you to think of a closed container. Okay, so this is a closed container. It's got 1, 2, 3, 4, 5 gas particles all moving at a specific speed. If I push down on this and make this smaller, make the volume smaller, the particles are still moving the same speed. They're just going to bounce off the walls more. So I'm going to have a higher pressure. So if I half the volume of the container, I'm actually going to double the pressure, which you can see here. If I have 1 liter and 100 millimeters of mercury, if I half the size of the container and go to 0.5 liters, the pressure is going to double. So this is an inverse relationship. The equation for Boyle's law, once we do a little bit of rearranging, is this: P1V1 equals P2V2. That means that the pressure, your initial pressure times your initial volume, is going to be equal to your final pressure times your final volume. Because if you look at this, as pressure goes up, like say pressure has to get higher over here, volume is going to have to go down so that this value equals this value. So this is our inverse relationship. So if I were to graph this, I would get a nice pretty graph like this, volume and pressure. As one changes, the other one goes down. Okay, so volume goes up, pressure goes down. So this would be a negative slope, and this is what an inverse curve looks like. You will see one of these in the lab. And so one example I want you to think of when you're trying to remember these laws would be like a syringe with a stopper. This is my little drawing of a syringe. As you push it down and make this part smaller, okay, so there's a stopper around here, you're going to have a higher pressure, smaller volume, higher pressure. You can also think of one way to remember this is Boyle's law. I think of Boyle's and bottle, a water bottle. If you are to squeeze it and twist it, right, make the volume smaller and smaller and smaller, eventually the pressure is going to build up and pop that cap off. So a smaller volume as you squeeze it is a higher pressure. Okay, so example number 1 is an example using Boyle's law. It says calculate the volume. So I would call that, we're obviously looking for a V value of a sample of gas at 575 atmospheres if it occupies 5.14 liters at 2.49 atmospheres. So hang on, I'm going to erase this and do it with you. Okay, so any of the problems in this unit, there's going to be a lot of numbers. So this is the way that I would approach them, and I recommend you do. I'm going to look at this problem. I'm just going to pull out all the numbers. I'm not even going to read the problem yet. I'm going to pull out all of the numbers. So I have this number, and this number, and label them. What are they? What variables are they? Okay, so I have 5.75 atmospheres. 5.14 liters and 2.49 atmospheres. Okay, so sometimes I'll tell you this is a volume or this is a pressure, blah, 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 blah. But the easiest way to do it is just to look at the unit. Okay, so atmospheres, I know that is a pressure. Liters is going to be a volume, right? Volume, liters or milliliters. And this is also a pressure. So what I want you to notice about this is I have 2 pressures. So that means I'm going to need an equation that has 2 pressures in it. Now, our only one so far is, of course, P1V1 equals P2V2, but that's going to help you out when all you have is your equation sheet. You're like, oh, I need something that has 2 pressures in it, a P1 and a P2. Now, the other important thing is that you label the right ones as 1s and 2s. Now, the 1s and 2s don't necessarily matter, but you have to put the right ones together. So, for example, it says calculate the volume. So that means I am looking for a volume. So I'm like, I'm looking for a volume of a sample of gas at this. So I'm looking for the one that goes with 5.75. So I'm going to call those my 1s. I'm looking for that one. It says if it occupies this much at this pressure, so that means those 2 go together. Again, which ones you call your 1s and 2s doesn't matter. I could have switched my 1s and 2s, but they have to be with the correct one. The other thing that you have to take into account is that they have to be in the same units. So if both my pressures are in atmospheres, I'm fine. They just have to match. It doesn't have to be in a specific one. I would be like, okay, I got P's and V's, so I need Boyle's law. So I would be like, okay, P1 V1 equals P2 V2, and then just plug in and calculate. So P1 was 5.75 atmospheres. Now I'm going to keep my units in here. You do not have to in your work, as long as you make sure your units match. Okay, I got 2.49 atmospheres is P2 times V2 is 5.14 liters, and then just solve for V1. Okay, so I would get for V1, answer is, I got 2.23 liters. Feel free to check my math, but you would just do multiply the right side and divide by the left side. So that would be your answer. Okay, and I would kind of take that same approach with almost every problem in this unit. Read it, be like, okay, this is what I have. This is the equation that I need. So print off the equation sheet, and then you can go ahead and calculate. Okay, on to law number 2, which is Charles' law. Charles' law has to do with temperature and volume. Now, remember, I told you the only inverse one you need to know is Boyle, so the rest of them are going to be direct relationships. So if you think about it, temperature and volume, as if I have a container that is flexible, right? It can change volume. If I heat it up, all of these particles are going to be moving faster. The way we represent that is by using longer arrows to show their movement. So if they're moving faster, they are going to expand. So I'm going to have a higher volume, right? So if temperature increases, volume increases, and vice versa. So both increasing means a direct relationship. So the equation is actually going to look a little bit different than what it did for the Boyle's law one, because if volume increases, then this value is also going to have to increase so that it equals what is going on the right side. Okay, so volume goes up. That means that this also has to go up so that they match. Okay, so direct relationships are going to look more like this. V1 over T1 equals V2 over T2. Now, if I'm in the lab and I graph this, I'm going to get a nice, pretty straight line. As the temperature increases, the volume increases. This is how your direct relationships are going to work. Again, you will see this in the lab. Now, one thing to keep in mind for this equation is that your temperature must be in Kelvin. Okay, temperature and volume are directly related in Kelvin temperature, but because Kelvin is a specific measurement of how fast the gas particles are moving. If you use Celsius, because of the way the conversion works, it is going to make your answers incorrect. So before you plug things in, they have to be in Kelvin in this unit. Have to. Okay, if you plug in Celsius temperatures, it is not going to work because of the way this works. You will see that in lab as well. So this is the conversion. So if I do ask for Celsius or I give you a temperature in Celsius, which will happen because we use Celsius a lot to measure temperature, you do have to be able to convert it to Kelvin before you plug it in. So just add 273.15. Okay, so the example I like to think of with Charles's law is a hot air balloon. Okay, a hot air balloon, as we heat up those gases in the balloon, it's going to expand, which is why it will then float, because then you have a lower density, but it just expands that balloon. Okay, so hot air balloon goes with Charles. And so I'm not going to walk through specifically example number 2 here. You guys can do that. I pulled out all of my variables. I have 29.1 liters. That is a volume because it's liters at 0 degrees Celsius. That is a temperature. Okay, so I have my V1 goes with my T1. Now I went ahead and converted it to Kelvin. So these two go together. So those are my ones. What is the new volume? So I'm looking for V2 when it is heated to 15 degrees Celsius. So again, I went ahead and converted that one. That's my T2. So I have 2 temperatures and I'm looking for a second volume. So I know I need to use this equation. So I plug in V1 over T1 equals V2 over T2. You can cross multiply or however you want to do your algebra to get that V2 is 30.7 liters. Okay. On to the next one. So we got 4 total. We have Gay-Lussac's law, which is temperature and pressure relationship. Again, a direct relationship. If you heat something up, those particles are again going to be moving faster. Like I told you, the longer or bigger the arrows, that means they are moving faster. So of course, the pressure is going to increase because they're going to hit the walls of the container more and more and more. So the equation looks very similar to it than it did to Charles' law. So it's pressure 1 over temperature 1 equals pressure 2 over temperature 2. P1 over T1 equals P2 over T2. Again, you have to be in Kelvin or you will get the incorrect answers. Get a nice pretty graph like this for our direct relationship as temperature increases, pressure increases. And then an example I like to think of is car tires, right? In the summer, your pressure is high, okay, because it's hot outside, so those particles are moving faster. But as it starts to cool off, you might get that little ding, ding, ding in your car saying, oh, you need to go put air in your tires. And that's because in the winter, as the temperature drops, the pressure drops. That doesn't mean like you lost gas particles necessarily. It just means that they're moving slower in there. So there's not as much pressure. So you have to put air in your tires in the winter generally because the pressure decreases with the temperature. All right, example number 3, I highly recommend pausing and doing this one by yourself. So pause it right now. Okay, and then I'll walk through it. So a sample of gas has a pressure of this, I know millimeters of mercury, at 18 degrees Celsius. So I have a pressure, I have a temperature, go ahead and convert it to Kelvin, but you don't have to convert the pressure as long as both pressures are in the same unit. So what temperature will the gas have if the pressure is increased to this? I've got all my values here, plugged them in. Now I recommend doing a cross multiplication if you know how to do that. This times this divided by this will give you your T2, which I got is 405 Kelvin. I didn't specifically ask you to convert it back to Celsius. You could, but I didn't. Be careful with your algebra here. This is the most missed algebraic step. So if you need help with this, please let me know. All right, last empirical gas law is Avogadro's law. This is amount of gas and volume. This is like the easiest law, right? Also direct. It means the more gas you have, the larger space it takes up. So 1 mole of gas, a balloon would look like this. If I doubled the amount of gas, the balloon would double in size. Okay, it's like blowing up a balloon. So the equation is V1 over N1 equals V2 over N2. Yes, we do use moles, just as all of our other things. So if I give you grams of something, you gotta convert it to moles, okay? We'll get a nice pretty line like this, moles versus volume. The more gas you have, the larger the volume that you have. An example, like I said, is blowing up a balloon. So if you're thinking of Avogadro's law, it's like blowing up a balloon. Putting more air into the balloon will make it larger. Okay, and this is going to be your equation. So the balanced equation with Avogadro's law. So I do want to talk, it's like a little bit of stoichiometry just for a minute, is that since it doesn't actually matter what the particles are, since volume and moles are proportional always. Okay, so more moles, higher volume, right? You can actually use a mole ratio just like a volume ratio as long as your temperature and pressure are constant. So this might kind of mess with your mind a little bit here. Let's look at this equation. Okay, this is a balanced equation. 3 H2s plus an N2 makes 2 NH3s, right? So I would read this as 3 molecules of hydrogen react with 1 molecule of nitrogen to make 2 molecules of ammonia. I can also read it, right, as 3 moles of hydrogen react with 1 mole of nitrogen to make 2 moles of ammonia. I can also read it as 3 volumes, let's say 3 liters of hydrogen, react with 1 liter of nitrogen to make 2 liters of ammonia. That one might mess with you. 3 liters plus 1 liter of this actually only makes 2 liters of this, as long as the temperature and pressure are constant. And that is actually true. That's actually what's going to happen, because if your temperature and pressure are held constant, the size of the container is going to change based on how many particles are in there. And the number of particles actually changes in this balanced equation. So if you are doing stoichiometry, which we will do a little bit later, if it's in moles and your temperature and pressure are constant, you can just go by volumes, which is kind of cool. So that's just kind of one piece of Avogadro's law. So example number 4 says, what volume in liters of water vapor, so it's water H2O gas particles, will be produced when 34 liters of hydrogen and 17 liters of oxygen react according to this equation below. So if you have constant pressure and temperature, like I just set up here. So if I have, I just wrote below this, I had 34 liters of this, I have 17 liters of this. Now, normally this would be like a limiting reactant equation, but I specifically gave you a 1-to-2 ratio. So this is the exact amounts you need. So if you react 34 liters of this with 17 liters of this, don't change the pressure, don't change the temperature. Since this is a 2-to-2 and this is a 1-to-2 ratio, you actually end up with 34 liters of your product of water vapor. These are not additive because they're not massive, they're not moles, or they are moles, sorry, they're just like moles. They're not additive like the masses would be, because we have containers, the volume can change based on the number of particles. And this is a really, if you're looking at a particle relationship, it's two of these and one of these makes just two of these. So the volume is actually 34 because it's based on the number of particles. Okay, so that might kind of mess with your mind a little bit, but if you're just using volumes, you can use that as a ratio, just like a mole ratio.